right, so now we're at a point in calculus where we're going to develop with a different concept of it. Everything we've done so far, particularly in a trigonometric point of view, has been with the unit circle. Meaning that if we were to take a look at sine, cosine, tangent, it's in relationship to a circle whose radius is 1, and where we can find the different points, and we can predict the value of the function, like for sine and cosine, in a what they call a sinusoidal graph, where it's up and down, up and down, up and down, repeating. Tangent, of course, is the S curve or S shape curve where we have asymptotes at various points and it's repeating that way. That's what their functions give them when you solve for y or f of x. The area of the circle that we looked at here can be defined as the integration for this top half right here, the positive part. That gives us the values that are the sinusoidal curves. Hyperbolas, however, is another idea. Now, this is brought about because not everything runs in circular motion. There are sometimes what they call a catenary motion, where you have this two set points in a kind of a hyperbolic shape of a cable connecting those two. And so it has a different scheme to it, rather than like the unit circle, where the unit circle is basically ideal, but this is kind of more realistic. And so the general formula for a hyperbola is y squared minus x squared equals 1. We can rewrite that so that y is equal to the square root of x plus 1, x squared plus 1. And then we to find the area of that, we're going to look at this area right here. So if this is our half of our hyperbola, the positive part, the other half is down here, but we'll just focus on the y-axis and the area between that and this, and we're going from -1 to +1 here. This is how we would find that value. And it turns out we don't get a nice smooth sinusoidal curve. We instead get something that is oddly shaped like this. So in the case of this scenario here, where we take a look at predicting the value of the function at a particular numerical value, whatever that is, this is the curve that we get when we look at the sine version of in hyperbolic function. We have this hyperbola here and this hyperbola here, and the sum of the y values as we go across looks like this. This is our shape of a sine curve wave in a hyperbolic function. We call that sine. It's spelled S-I-N-H, but it's sine instead of sine. And if this curve shape is the result of the function of y equals 1/2 e to the x power, and this one right here is g sub x, which is our y, is equal to -1/2 e to the negative x power, and we add those two together, this is what we get as a result. So we define sine of x as e to the x minus e to the negative x over 2. And for this function, the domain is anywhere from negative pi, or negative infinity to positive infinity. There's no limit for that, and there's no limit for the range. So that is what is defined as the hyperbolic function of the sine of x, or sine. And because of that, we can come up with all 6 trigonometric functions from a hyperbolic point of view, as opposed to a circular point of view. And for this one right here, it turns out that the cosine version of the hyperbolic function is the result of the sum of these two functions right here, which are defined by this, e to the x plus e to the negative x over 2 for both. So cosh, which is how they define that, cosine hyperbolically, is e to the x plus e to the negative x over 2. And now that the range is from 1 to infinity. So it doesn't even approach, 0 approaches 1 right here. And this is our result. Well, actually, this is the one right here. This is the two asymptotic curves of 0, but the sum together gives us this right there. And then, because tangent is defined as sine over cosine, then the hyperbolic definition is exactly the same thing. And it's going to give, this is the values we use for the tangent, the hyperbolic tangent, or as they call it, fan, or dan, of x, gives us this shaped curve here. And cosine is the inverse of that, and it gives us this value right here. And so this is our function. And all of these are in your book, and this will be provided for you on the test. So it's just a matter of you being able to interpret these values from that. This is an interesting side note, and I think this is kind of cool from a different point of view. And this is cosecant hyperbolically, so they call it cosec. And it looks like this, and it's 2. It's over e to the x minus e to the negative x. And then the sec, which is the inverse of cosh, because secant is the inverse of cosine, is equal to 2 over e to the x plus e to the negative x. It looks like this. This is our domain and range. So, how do we use this? Well, the problems that you'd be looking at are going to be designed like this. The shine of 3, the formula for that, we're just plugging the 3 for x. So we get 10.0, rounding out the 3 significant figures for this. The than of negative 2, just plugging negative 2 for the exponents, gives you negative 0.964. And then number 3, we get into the natural log of 2 for our x value. So we have 2 over e to the natural log of 2 minus e to the negative natural log of 2. We have to remember, though, that natural log means e to some exponent. So e to that exponent, the exponent for that is 2. And the exponent for that, the negative means it's the reciprocal. The negative exponent is the reciprocal, so that becomes 1/2. And that reduces down to 4/3. Cof of natural log of 5, same deal. The e to the natural log of 5 is just 5, that's the exponent. The negative exponent is negative 5, it becomes 1/5. And then we go through that and we get either 13 over 12 or 1.08. And if you want to use the decimal form up there, that would be 1.33. Either way is fine. Now, in Theorem 519 in your book, we are using inverse functions of hyperbolic functions, just like we did with circular functions, cosine, sine. So it's the same basic idea. You take the value or the formula for inverse cosine, which is this, so replace the x with 2. This gives us natural log of 2 plus square root of 3. And then we punch that into a calculator, we get 1.317. And the same with the sec, inverse sec, 2/3. The formula for that, again, through that theorem, plug in 2/3 for that, plug all that nonsense in, we get 0.962. Now the last thing I'll be asked to do is to verify trigonometric identities from a hyperbolic point of view. And for this, we're using the definitions of the functions y equals each of these values for tangent. And for or secant, only from a hyperbolic point of view. It's the same basic idea. We just go ahead and plug in these values, and this becomes a mathematical treat of multiplying or foiling out your components of binomials. So this is the than definition squared, and this is the sec definition of x. And then we want to prove that this all equals 1. So we go through mathematically. I pulled out a denominator, a common denominator, e to the x plus e to the negative x. So that's 1 on top squared, and everything else left over is e to the x minus e to the negative x times, or plus 4, 2 squared is 4 there. And then we went ahead and FOILed this out. And you look at this portion right here, when you do that, if you get 2e to the 2x, e to the negative 2x, remember when you multiply like bases, you're adding exponents, so that gives you e to the 0, which is 1, so that just gives you 2 there. Over here, same thing, this gives you a negative 2, plus 4 gives you, well, when I simplified this, I explained that, but when you add these two together there, you get 2. And so you get this fraction, which has this denominator, and this numerator has to be is exactly the same as this denominator. They cancel out, and that gives you 1. All right, so that's just how you verify that. The same thing with this. This is a rather interesting one. This is one of those trigonometric identities we dealt with at the very beginning of the second semester. We talked about how we have certain identities. In this case, it's the sum of 2 angles. But so what we're going to do is go through mathematically and resolve this and see if it's going to be the same as this, just like we did with the previous one with 1. So the definitions are applied here for each of those. And we go through and multiply everything out. And you get 2 fractions with denominators of 4 after everything's FOILed out. So I put the whole thing over 4, then I combine all kinds of stuff. So just mayhem ensues, and canceling out stuff, combining stuff, all that good stuff. But the important thing about this one right here is that when the smoke clears, a lot of this stuff just kind of gets, like I said, cancels or combines. And you end up with 2 times e to the x plus y minus 2e to the negative x minus y. This is an important aspect right here, because when you have that, you are now going to get a negative quantity x plus y for that exponent. It's real important you do that, because what happens here is when you look at this, you factor the 2 out here, 2 and 4 cancel out, gives you e to the x plus y minus e to the negative quantity x plus y over 2. And since we define shine of anything, I use z in this case, I could have used u, whatever, gives you e to the z minus e to the negative z over 2. That's the definition of it. And if z equals x plus y, then you can see that this becomes e to the z and this becomes e to the negative z, which means that you have the sum of 2 angles, and this is now verified. Okay? So, go ahead and do your fun exploring on this new concept, which I think is kind of a fun thing to do if you're into that mathematical thing. Have fun.